So I just start now, and my presentation will be in English, but you're welcome to ask questions in Swedish as well. So this was actually a very good introduction to our project, the CAPS project, and you probably will hear some of the aspects Håkan was already talking about. So, so this presentation will have two talks actually. So first I'm going to talk about paper-based supercapacitors, and then Nicklas will talk about the kinetic energy recovery system. So the CAPS project, CAPS is for kinetic energy storage in paper-based supercapacitors, and my part in this project is focusing on the paper-based supercapacitors, and we want to produce also large functional surfaces, and in this case we want to produce supercapacitors which have a high power density, a long cycle life, and which are cost effective. And we're focusing on inexpensive and environmental friendly materials, and also on inexpensive and large-scale production processes. So we try to combine good functional materials with large production processes. And the goal is to produce a supercapacitor that can deliver 60 volts, 50 watt hours, 15 kilowatts, and which is not too big, so it can be used in a car. So we want to have a device that is like the size of a car battery and weighs about 10 kilograms. And having this in this curse system, Nicklas we're going to talk about, we can save up to 10% of the fuel consumption of a car. But I would like to start with explaining you what a supercapacitor is. It's an energy storage device, and it's based on electrostatic charge separation. So it's similar to a battery, but the battery has chemical reactions involved, and in this type of energy storage device there are no chemical reactions. So a supercapacitor has two electrodes and the separator in between. And when you want to charge the supercapacitor, you have these ions in the middle, the negative and positive charges. And when you charge the supercapacitor, the positive ions will go to the negative electrode, and the negative ions to the positive electrode. And this is just a schematic example, but actually this is very close together. So the ions just move a very small distance. And this is a very fast process. The chemical reactions in a battery are actually very slow compared to these reactions, where it's a very fast, short distance that the ions are moving. And you can see this in the performance of the devices. Here you see the energy density plotted against the power density, and supercapacitors have a much higher power density than conventional batteries. But the batteries can store more energy. But however, in the application we are looking at, the curse system, we actually need a high power density. It's more important than the energy density. And what you also see is that a supercapacitor can be charged within just a few seconds. And this is important as well. But a battery is a very slow device, so it needs hours to be charged. And thus, supercapacitors are better in this application than batteries, but Nicklas will also talk about this. And our idea is to implement supercapacitors, but the problem today is that they are really expensive. And as Håkan also said, in electric vehicles we usually use batteries, but there are not so many electric vehicles on the market today because the batteries are so expensive and it's not very cost effective. And a supercapacitor can be produced much cheaper. And we had the idea to use inexpensive materials as paper, for example. And paper can be used as the separator in the middle of the device, but also as a substrate for the electrode material. And by using paper, which is inexpensive and environmentally friendly, we can also take these paper technologies, so proven technologies, which give us the possibility to produce large areas. And here's actually a picture of our first coating trial where we coated the active material, the electrode material, on paper. And here you also see some pictures, and what I want to say here is that it's one part of this project is to produce these materials, to optimize them, but also to develop a coating process. And here we go from small lab scale, as you see in the left picture, where we filtrate the electrode material on paper, to some larger process where we actually have a big roll-to-roll process, a fast process and a large-scale process. And when we now look at our supercapacitor we are producing and compare it to a supercapacitor that is available on the market today, we see some good and big differences, good for our application. And here I compare the Mid-Sweden University capacitor with the commercial product, and as you see, voltage, current, capacitance and the energy is the same. And when you compare the size of the device, here measured in liters, see that our device is much smaller, and this is important for the car industry, but also it's much lightweight. It's 10 kilograms compared to 15 kilograms. And another important fact is the cost, of course. And we calculated the material cost for our device, and it's approximately 500 Swedish crowns. But the commercial supercapacitor, which has the same performance today, is about 33,000 Swedish crowns. So here you see the potential of our device. And I think Nicklas is keen to talk more about the kinetic energy recovery system. So.
Jag byter till svenska igen. Hoppar över till vår applikation. Det vi försöker göra alltså är göra pappersbaserade superkondensorer som vi sedan kan använda i ett bromsenergiåtervinningssystem. Och ett bromsenergiåtervinningssystem, det är istället för att använda sina friktionsbromsar för att bromsa sin bil, det blir bara värme, energin försvinner, så använder man sig av en generator som konverterar bilens kinetiska energi till elektrisk energi som man kan då lagra i en sån här superkondensator. Det gör fordonet mer energieffektivt och man kan spara både bränsle och miljö. Vårt mål med projektet är minst 10% och inte upp till 10% bränslebesparing, men teoretiskt kan man spara upp till 25% i stadstrafik. Vi fortsätter. Ett sånt här system har ju vissa krav. Ska vi kunna göra fordon mer energieffektivt så måste vi ha hög effektivitet i vårt system. Det måste klara höga strömpulser, alltså hög effekt under väldigt kort tid. För när du bromsar med din bil så blir det väldigt hög effekt, men du bromsar bara mellan 1 och 5 sekunder. Batteri är väldigt svårt med det, så det är en ganska långsam process. Och det måste vara kostnadseffektivt. Det måste finnas ett ekonomiskt incitament för att skaffa ett sånt här system. Så är det för dyrt så kostar det mer pengar än vad vi kan spara, så att säga. Energilager i det här fallet måste kunna laddas väldigt, väldigt snabbt. Måste ha en god cyklingsbarhet, alltså livslängden i det här. Vi har sagt att minst 500 000 laddcykler måste den här klara av. Det motsvarar ungefär 3 år i stadstrafik, med exempelvis en budbil. Ett bra batteri idag klarar ungefär 2000 cykler. Så därför har vi valt att satsa på superkondensorer när det gäller den här tekniken. Idag är superkondensorer dyra, som vi ser. I alla fall marknadspris, men de har också ganska mycket dyra processer och använder dyra material jämfört med oss. Så vi borde kunna få en billigare superkondensator. Våra kondensatorer består av papper, kol och saltvatten. Vi har en egen process där vi skjuvar sönder kolet till nanomaterial för att få stora ytor i våra elektroder. Och vi använder befintlig pappersbestrykningsteknologi. Och det borgar för att vi ska kunna få en billig process och miljömässigt hållbar process också. Sen tillsammans med STM-Tech så utvecklar vi då en fordonssimulator, en fysisk fordonssimulator där vi kan montera våra superkappar i slutändan och utföra massa tester. Då kan vi testa våra kondensatorer efter verklig körning. I princip tar man en bil först och kör på gatan och sen loggar man hur man kör och hur mönstret ser ut. Och sen stoppar vi in det i vår simulator och sen så laddar vi ur vår kondensator efter verklig körning. Då kan vi jämföra med kommersiella produkter. Och vi kan utvärdera hur bra effektivitet har det här systemet. Hur mycket bränsle kan vi spara och hur kan vi påverka avgasemissionerna på bilarna. Så det är vårt verktyg då för att kunna utvärdera våra kondensatorer. Nu tror jag att tiden börjar bli knapp, så vi tackar för oss. Och det här är namnen på de som är med i vår forskningsgrupp. Och våra samarbetspartner är STM Tech, Boredins stiftelse, Länsstyrelsen Västernorrland, Energimyndigheten, Superior Graphite, SCA och Nordic Paper. Tackar! Så, bra.